Okay. In that case, before we consider, okay, if light is a particle, then it should behave like a particle when it collides with other particles, right? So we're going to consider the collision or scattering of light with other quantum particles. By quantum, I mean microscopic. Because we haven't really established that what quantum is. We only know so far kind of a vague definition of what quantum is, right? We don't really know exactly what quantum is. So microscopic is probably a better term. So let me just put this in bracket and the other one not in bracket. So before we do that, let's consider how classical electromagnetic waves interact with a free electron, okay? And then we will basically have to compare it to the experiment. And if it matches the experiment, then of course classical physics is a good description. Otherwise, it's not, okay? So the picture that we have is that suppose that we have a free electron sitting in space. So it's not moving, it's stationary. And we subject this electron, so this is and suppose we subject this electron to a wave of light. We shine light on it. And the direction of propagation of light is this. So then it should be clear that the electric field is in direction transverse to the propagation, and therefore the electron will be subject to an electric field in that direction and this direction, right? And therefore the electron will start oscillating in those directions, right? So these are the directions of oscillation. But the electron itself is a charged particle. And when a charged particle oscillates, that is, it necessarily accelerates because oscillation means a rapid change of its velocity. It should itself emit radiation. So the electron itself starts emitting radiation. So now so this is radiation. So now the frequency of the emitted radiation is equal to the frequency of oscillation, right? Because it's a small antenna of sorts, and which is equal to the frequency of the incident wave. So this is a very long-winded way of saying that the light that we shine on the electron gets scattered. Some of it gets scattered, okay? But remember that light also carries momentum. Do you guys know what the momentum of light is? Right, so if its energy is E, then it's PC, right? It's related to the energy by PC. Because if it was a massive particle, then it would be P squared C squared plus M squared C4 square root, right? But light has no mass, so. Okay, so anyway, that's a segue. That's a diversion. But even in classical electromagnetism, light carries momentum, and therefore, what will happen is that the electron will start accelerating in that direction. It'll start moving, right? Because it'll absorb momentum from the incident wave. So now, in the electron's reference frame, what happens to the frequency of the incident light? Does it go up or does it go down?
It goes down.
Or stay the same? Sorry?
It goes down.
Right, because of Doppler shift. So the incident wave is redshifted, right? Therefore, the electron sees a lower frequency. Of course, the speed of light doesn't change, right? Because according to relativity, the speed of light is the same in all reference frames, all inertial reference frames. And therefore, its frequency must go down. So that means that the frequency of the emitted waves, emitted by whom? By the electron, will also go down, right? And this process will continue until the whole incident wavefront passes through the electron. So what do we expect to see? So what do we expect to see in terms of the scattered radiation? Can someone guess?
I didn't get that last sentence. Whole incident wavefront passes through the electron.
So basically, we are seeing that the electron is going to start accelerating, right?
Yeah.
And therefore, it's going to see a redshifted incident wavefront.
Okay.
And therefore, it's going to the frequency of its oscillation will also be reduced.
Yeah.
And therefore, the frequency of the emitted wave will also go down.
Yeah.
And this will keep on happening until the whole incident wave passes through the electron.
Oh, okay.
So during this time, what can we expect to see in terms of the scattered wave from the electron? Give me a guess.
A new light with lower frequency than the incident light.
But it'll start at the start the scattered light frequency will be equal to the incident light, right?
Yes.
But at the end, the frequency of the scattered wave would be less, right?
Yes.
So we would expect there to be a whole range of frequencies in the scattered wave, scattered light, right?
Got it.
Yeah, makes sense.
Right. So what do we expect to see? We expect to see a whole range of frequencies in the scattered light. Okay.
The gradual decrease of frequency, would it be continuous or discrete?
It should be continuous, right? Because the electron is accelerating continuously, right? As it's absorbing more and more momentum.
Okay.
It's continuous, and that's what the range means, okay? But in reality, what one sees is the following. In experiment, one sees that the frequency of the scattered light depends on the angle of scattering. Okay, so what can we deduce from that? It's not something that is easily explained, or it is not something that can be explained from classical physics. But if you think of it, of light as a particle, then it seems something very plausible. Why is that? Because remember, Einstein proposed that light has energy E nu. So suppose that light was a particle and it's coming in like that, and we have our electrons sitting here, and there is some collision, and light kind of gets scattered in that direction. And the electron recoils and gets scattered in some other. The angles are not correct, but whatever. Okay. So depending on what angle the scattering happens, of course, the energy absorbed by the electron will be different, right? Because intuitively, if, suppose the scattering, the backscattered light would impart the most, amount of energy to the electron, right? So it is plausible to think of it. So if we think of it as some sort of collision between two particles, then the angle of the collision can explain its energy. And because the energy is dependent on the frequency of light, therefore, we can expect the frequency to be the frequency of the scattered light to be dependent on the angle. Okay, so this is the heuristic idea.
So you're saying the wave idea cannot explain this, but the classical idea of particles can.
It's not classical because I'm using the quantum expression here.
I mean the ball hitting on another ball analogy.
Yeah, that plus this sort of quantum input. The rough idea of some sort of a collision is something that is plausible.
Can I ask what are we trying to do here by this?
We are trying to figure out a way to see if the collision picture gives us a way in which the frequency of light is dependent on this angle. The frequency of the scattered light is dependent on this angle. And what I'm saying is that since the scattering, the direction of scattering should be related to how much energy the scattered light has, therefore, it should also, the frequency should also depend on the angle. Right? I mean, think classically. Suppose you have a baseball here, right? And you throw a golf ball towards it, and the golf ball hits this end. Then the golf ball will be it'll be deflected, but the energy that the golf ball will impart to the baseball will not be the most amount that you can impart. Whereas if the golf ball, hit the baseball here, and it bounced back in that direction, then it'll have imparted a lot more kinetic energy, right? So all I'm trying to say is that the idea of collision has built into it that the direction of scattering is dependent on how much energy the scattered particle will have.
Okay.
Right. So this is the rough idea, and now we are going to make this quantitative. Okay. And the quantum version of this is called the Comtone effect. So what do we need to study this effect? Well, we already know E is h nu, but we also use the fact that the energy of a wave, this is borrowed from electromagnetism, is P times C.